Now start running through the talk. So thank you very much for attending our afternoon talk. My name is Nick Webb and I'm a lecturer at the Liverpool School of Architecture, University of Liverpool. And my research investigates the use of digital tools in a historic context. And I'm joined today by Alex Buchanan, who's a senior lecturer in the Department of History, also at the University of Liverpool. And Alex's research is at the intersection between architectural history and archive studies. And she's previously touched on the study of medieval vaults in her research. So today we want to talk to you about some of our findings in relation to vaulting. Vaulting is an arch ceiling construction, usually made of stone, sometimes made of wood. And today we want to talk to you, obviously, about the context of Nantwich St Mary's Church. So this is a map of our site. So Alex and I met in 2014 after a bit of academic matchmaking via a colleague. So the project team began with Alex and I, and we were joined by J.R. Peterson, who is a technician in histories, languages and cultures. And we put in some funding with the Paul Mellon Centre for Studies in British Art to enable us to produce a digital scan of Wells Cathedral. But because we're based in Liverpool, and this was our first attempt at using digital tools in this context, we wanted to look for a local pilot study to test our methods first before travelling all the way down to Wells. And we ended up with two pilot studies, one being Chester Cathedral, the other one being Nantwich, which we're obviously talking about here today. So it was on Friday the 13th of November 2015, we travelled down to Nantwich with our scanner and produced a scan of the East End, basically the chancel and the north transept. So although we only intended Nantwich to be a pilot study, it actually became one of our major case studies for our research, and that's included in our upcoming book. The project, as you can see by the list of sites on the left, the project expanded quite considerably. And in 2018, we received a grant of nearly £250,000 with the Arts and Humanities Research Council. And this enabled us to add two further people to the project, Dr. James Hilson and Dr. Sarah Duffy. And that round of funding also facilitated these talks and workshops that we're starting today. So you're our first talk. So why are we studying medieval vaults using digital tools? Well, in 1841, Professor Willis, who was a scholar at Cambridge and an engineer, he gave a lecture to the newly established Institute of British Architects. And at this talk, he outlined his theories on how vaults were designed and constructed. And he based his findings mainly on accessible vaults, such as cloisters, which are relatively low to the ground, as well as destroyed vaulting, such as parts of Canterbury Cathedral. So you can see here, I've just highlighted at the bottom. This is the cloister at Norwich. It's one of the sites that we visited. And these are pretty much, well, they're very accessible. And this is one of Willis's case study sites. It's only 4 meters at its apex from the floor level. Here's people for scale, just so you can see how big some of our sites are. And here's Nantwich. So Nantwich in the chancel, it has an apex at about 11 meters above floor level. Exeter, this one's around 20 meters above floor levels in the high vaults. And then we get all the way up to Ely at the Lantern, which is a whopping 44 meters above floor level. So what we're trying to show here is how difficult it would have been to study these structures given their scale. So as we're trying to point out, many of these vaults were inaccessible to Willis. So he was using his talk to the Institute of British Architects as a call to architects. If you're putting scaffolding up, if you're making amendments to these buildings, let me know so I can gather my data and further explore vault design. But he had little success in this regard. Also, we have to call into question the accuracy of previous surveys. So if these are produced using analog methods, we can't be sure that they were recorded properly. So skip forward 180 years, we still don't fully understand how vaults were designed and constructed. But using digital methods, we can create very accurate models of these and begin to analyze them digitally. So I'll now hand over to Alex, who will start to introduce some of our research questions and the history of Nantwich.
Thank you very much, Nick. So I know many of you come from Nantwich and all of this will be very familiar to you, but for those of you who are joining us from further afield, a little bit of background on the history of St Mary, Nantwich. It's largely undocumented as a building, so its architectural history is very reliant on archaeological evidence. The church was founded not as a parish in its own right, but as a chapel of ease to the nearby parish church at Acton, which enabled those people living in Nantwich to attend services more locally. Both of these churches were in the patronage of Combermere Abbey, meaning that the vicar of Nantwich was appointed by the monastery. The church was built in the late 13th century, but what we see now has been substantially reworked on the same foundations. It's in very ambitious scale. You can see it's a cross-shaped church, and the fact that it has a vault at all is unusual in parish churches. But the initial ambitious scale may be attributed to patronage by Robert Burnell, who was Bishop of Bath and Wells and Chancellor of England, one of the really rich men of 13th century England. Rebuilding of the building started in around 1340, when the chancel was remodelled and the north transept was extended. But work was probably halted by the Black Death in the years around 1347 to 8, and only recommenced in around 1380. And the completion process may have been very protracted and possibly not completed until the early 15th century. We therefore wanted to know what our data could add to the understanding of the church. Given that the vault was obviously the last part of the chancel to be completed, we wanted to understand the relationship between the existing architecture, commenced in the 13th century, and the design of the vault. Next, we wanted to know how the vault might have been designed in both 2 and 3 dimensions. Then we wanted to know how the design related to other 14th century vault designs. And finally, when construction broke off in around 1350, the vault of the north transept was left unfinished, but for the springing stones. So we wanted to know whether these could be used to work out the intentions of the original designer. But first, we needed to decide how we would capture the data we needed to answer these questions. And I'll now hand back to Nick for this part.
So in our research, we've investigated 3 different methods, these being total station, laser scanning, and photogrammetry. So the first of these, total station. The way this works, you can see me in the image here. This is at Chester. You look through a viewfinder, and guided by a laser, you find a position in 3D space that you want to record. You press the side of the total station and it records that point in space. And when you're surveying a particular part of a building, for us, this was vault intrados lines, the outermost edge of the ribs. It builds up almost like a dot-to-dot plan that you can see here in the central upper image. So what are the advantages of total station? Well, the data is precise and selected. You're only recording what is required, but that can also be a disadvantage. Because, for example, if you want to record the webbing, which sits in between the ribs, then you're going to have to use a separate campaign to record all of that. Disadvantage as well, the scanning times are long. So to scan 1 vault bay, it typically takes us about 2 hours using total station. And finally, the disadvantage is that the results aren't in color. They're literally points in space that we get out of this data. Moving on then to laser scanning, this is a more advanced version of total station. So rather than recording 1 point between it and a point that you choose, it records the distance between it and every solid surface that it hits, and it does this hundreds of thousands of times over. The scanner also takes a series of photos at the end of its run and is therefore able to assign color to each individual scan point. And the analogy that we use is you end up with something called a point cloud model, which is almost like a swarm of bees, but in the shape of a building interior. So you can see the type of results that we get in the center here of this image. So the plan has now got color on it, and we're showing the entire vault. So what are the advantages? Well, laser scanning is precise and it records everything in the vaults and the wider interiors. So although we're studying vault design, it's also recording the window details, the floors, the rest of the elevation. So if we were doing further studies, we could be investigating these too, because it's all there in the data. It's also relatively fast. Typically, we do a 10-minute scan or a 30-minute scan, depending on the height of the vault. So the lower the vault, the less time it takes. Disadvantages, though, you end up with very large file sizes and you need a powerful computer to be able to do anything with the data. Another disadvantage is that the software and the hardware is very expensive. You're looking at about an investment of £50,000. So using this data, these point cloud color models, you can export ortho photos. This is where perspective is removed to create an orthographic plan and section. So you can see an example of a plan, top center here. And we can also export mesh models, and that's where the points are converted into surface models. So you kind of join all the dots of the points into triangular surfaces. And an example of that is shown at the bottom here in the center. The third method that we investigated was photogrammetry. So the way photogrammetry works is that hundreds of photos are taken using a digital camera from as many different angles as possible to ensure that all details of the vaults in our case are captured. And here you can see JR, one of our technicians, taking photos, this time at Wells Cathedral. And if you look carefully to the bottom of the image, it's being carefully watched by the cathedral cat. So as you've taken all the photos of the object you want to capture, you then put this into a clever piece of software which can work out the perspective of where the image is taken from. And it builds up a 3D model, again in a point cloud format, so lots of points in space. And likewise, you can then create similar outputs, ortho photos and mesh models. So what are the advantages of photogrammetry? The first one is that it's inexpensive. So all you need is your own digital camera or even your camera phone if you have a smartphone, and a copy of the software, which is about £500. It outputs very high quality images, and we'll talk more about that in the next few slides. But the disadvantage is that sometimes the quality of the data can be poorer as you move far away from where the photo has been taken from. So we'll just look at that in a little bit more detail. This is, again, an ortho photo. So the plan view, like an architect would use when designing. A plan view, this time of the Lady Chapel at Exeter, as a result of laser scanning. And you can see the geometry looks pretty good here. However, the image is a little bit grainy. And when we compare that to the equivalent produced using photogrammetry, again, the geometry is looking pretty good. And the image is exceptional, so it's a better image than we see in laser scanning. But then we wanted to investigate, what does that mean when you investigate the details? So here we can see a column that's being taken as a section cut through it. And we can see a version produced with a laser scan on the left and photogrammetry on the right. Crucially though, this was taken at a low level, so about a meter above the floor. This meant that the camera for photogrammetry, you could take the photos relatively close to that column, and likewise the laser scanner is on the floor, so it's quite close to that column. But when we then look further up, so this is looking at a rib profile, so probably about 10 or 11 meters above us, we start to see some issues occurring with photogrammetry. So if we look at the first two images on the left, the second one along shows a rib cut taken through the vault using photogrammetry, and the clarity of that cut is pretty poor, whereas if we look at the same cut taken using laser scanning, we still get a pretty good record of that profile. So because of this, we therefore decided on laser scanning as our main method of surveying medieval vaults. So this is the crucial point. Laser scanning, you get really good results even if you're 20, 30 meters away. So we get really good, reliable data, whereas with photogrammetry, it's not as reliable, particularly when looking at details. So once we have the data, we'll just talk through a little bit about laser scanning. So here you go. This is actually at Nantwich in the chancel. As a time lapse, Alex is talking to members of the public. The laser scanner, if you look, it's spinning very slowly there in the center. So we just have to check that nobody trips over that. JR's taking photos for photogrammetry. And basically we spend hours doing this. We're kind of in churches and cathedrals for a few days. So once we've taken the laser scan, we have to then do a process of registration. Laser scanning, photogrammetry, total station, it all works on line of sight, i.e. if you cannot see the target, the scanner cannot see it either. So in order to capture all of the data, you have to take more than one scan. We tend to find for our research that one scan per bay is enough. So if you look here at the different colors shown in this example, there's one bay, the fourth one along, that looks predominantly blue, but you can see further to the right of that, there's also a lot of blue that's been captured there. So it's the overlap of the scans which ensures that you get a really good model at the end of it. And at Nantwich, we took a total of 11 scans. So these are some of the outputs that we get. So looking at in a bit more detail, but focusing on Nantwich now, these are the ortho photos. So you can see we have the chancel here and the crossing. So the plan to the bottom and then a sectional view to it above. And that's an example of the type of data that we get out. And we also have 3D models. So this is one of the bays in the chancel. This is available for you to have a look at online. We'll send links later in the talk. So this is just zooming in now, and we'll show you the buildup of the mesh. So rather than being a point cloud, this is a triangulated surface. So if we look closely, hopefully you can now see how that's all made up of these triangles. Okay, so now we're at the point where we have our models and we want to start analysing them. So a key point for us in our research has been the intradus line, and this is the outermost edge of a vault rib. This is really critical because when the vaults were being built, you would have first put up timber centering, which is to the design that's required, and then on top of that centering, you would place along it the elements in stone that are going to be built, and then you wait for it to set and you take out the timber centering below. So the intradus line can tell us a lot about the geometry of a vault. So one of the first things that we do is we trace along all of these intradus lines, as you can see in this central image on the right. So we go through, trace each individual line. We can project out from that sectional views and plan views. But most importantly, though, we have these traced individual ribs, as I said. So once we have the traced lines, we first convert them into best fit arcs. Because of the fact that the tracing process, and we'll show you this in a video in a second, but the tracing process is almost like a dot-to-dot puzzle. So the first thing we do is create a best fit arc. So it's a piece of true geometry, and that then gives us some key geometry to work with. The first one of these is the impost, and this is the point on which the springing point of a rib appears to rest, and it's usually the abacus of a capital in medieval vaults. So here we can see down here the impost line. The next is the springing point. So that's the point here marked by a cross, and that's the lowest level of the rib where it departs from the underlying supports, and it's almost always a fixed point. The next is the apex, which is a notional point, and it's the highest level of the rib, and it's usually covered by a boss. The next point is the radius. So you can see here, we can extract the radius of each arc. And then finally, we have the center point of that arc and its relationship to the impost line. So they're the four key pieces of geometry. And I'll just conclude this section by showing you a video. This is at Ely in the North Choir Aisle. So this is one of the ways in which we trace over those mesh models. So you can see we're just moving along the intrados line here, trying to find the center of it. More recently, we use automatic processors for this. So we take section cuts through the data. Sometimes if the rib isn't straight, we have to revert back to this method. So there's a bit of a Blue Peter moment. Here are all the other ribs that have been traced. And as I mentioned before, the next step is to then create a best fit arc through that. So we're just telling the piece of software, it's called Rhino. So asking Rhino to turn the points on, and then we're asking the software to create a best fit curve through those traced lines. And now we can see those shown in purple. So the next thing we do is we trim down that circle that's been created, and we trim it via the impost line, which is shown in green here. And we also trim it at the notional apex. So now we've got that trace data, and over the top of that, we've got all of our best fit arcs. So now we start asking the software for some of the data. So we'll ask it for the radius. And we're getting a radius there of about 3.5 meters. And we start to put this into a data table. So you can see here, we have this really complex data table showing all of the different ribs and all of their properties in terms of geometry. So we ask for the center point as well, so we can measure the distance between the arc center and the impost line. And we put that back again into our data table. And then we also do the same again with the apex height. So I'll just stop that one there, and we'll move on to the next slide. And I'll hand back to Alex for this.
So first of all, let's look at the anatomy of a vault so we all know what we're looking at. A Gothic vault's got two main elements, the webs and the ribs. The webs, or the surface of the vault, were usually constructed from coursed masonry and plastered. In the Middle Ages, the webs could usually have been decorated with frescoes, as we still find in Italy, and remains of these survive in some English vaults, such as those at Lincoln Cathedral shown on the slide. So a church like Nantwich would originally have been in glorious technicolor. The ribs are the mouldings which usually mark the changes in plane of the webs, but they could also decorate planar surfaces. The ribs were built first as a framework, and the webs were added afterwards, but both elements are equally important to the structure of the vault. Medieval vaults aren't like modern steel frameworks infilled with non-load-bearing panels. The starting point of a rib is called its springing, and the top is called its apex. At the apex, where a rib meets another rib, as Nick's mentioned, there's usually a sculpted boss, and the bosses at Nantwich are very beautiful and can be examined using the mirror on a trolley, which the church has helpfully provided. Architectural historians have given ribs different names based on their location. The wall ribs mark the junction of the wall, and the transverse ribs span between side walls, marking the division between the bays. A bay is a compartment of vaulting, and the chancel vault at Nantwich has three essentially similar bays. Diagonal ribs cross the bay diagonally, and ridge ribs run along the crown of the vault, either east-west, which is the longitudinal ridge rib, or north-south, which is the transverse ridge rib. Additional ribs, which spring from the corners of the bay and rise towards the ridges, are called tiercerons, and those which don't start at the corner of the bay but start from another rib are called liurns. And a complex vault, like that at Nantwich, has all these elements. We believe from our research overall that medieval architects started to design a vault by creating a plan of the ribs in 2 dimensions. This was laid out full scale on a flat plaster surface called a tracing floor. Very few of these tracing floors survive, although they are recorded in medieval building accounts, and we've been lucky enough to be allowed to scan the tracing floor at Wells Cathedral. From our data, as you've seen, we can create absolutely accurate 2-dimensional representations of the vault, from which we can start to hypothesize the process used to draw out the plan on the tracing floor. We know that the drawing tools available to medieval designers were limited. Their main tool was a set of dividers or compasses from which they could create curves. They also had squares for creating angles and straight edges for drawing straight lines. So any design process we suggest, it has to be possible using only these basic technologies. And in our workshop in 3 weeks' time, we'll show you in more detail how to use these basic tools to lay out a medieval vault. So what we're presenting now is just a quick taster. The first stage was to lay out the plan of a single bay. At Nantwich, you'll remember that the plan of the bays was laid out in the 13th century. It was established by what we call the medieval golden section, or root 2 rectangle. If the shorter side of the bay is drawn as the edge of a square, the diagonal of that square is the length of the longer side. The next stage was to divide the bay into quarters. This can be most readily achieved by creating chevrons across the bay. Creating chevrons in both directions creates what's been called the starcut, which our research has identified as a key design tool for medieval architects. For Nantwich, a further diamond shape is then added. Intersections of lines drawn in this way establish the position of all the bosses and the location of all the ribs. We then overlay our hypothesis over our original trace data to check their conformity. And we're very confident in this case that it represents a good match. As I've mentioned, we found the starcut in use at other sites. Its benefit was that it enabled a design to be transferred between bays using proportions rather than measurements. This was vital because medieval churches were rarely constructed to the same accuracy as our scans. So any design had to be sufficiently flexible to be applied to bays of slightly different sizes. In the absence of accurate numerical measuring devices, using proportions would have been much simpler. The starcut could be used to divide a 4-sided bay into any fractional proportions up to 100ths. And so far we found thirds at Lincoln Cathedral, 6th at Wells Cathedral, 9ths at Exeter Cathedral, as well as 5ths at Lincoln, 7ths at Wells, and 13ths at Ely. The use of the starcut at Nantwich places Nantwich's design well within the mainstream of medieval geometrical design practices. Previous scholarship has identified similarities between the designs of Nantwich and the side aisles of the choir at Wells. Our research has confirmed these parallels, but it suggests that they could just as easily have been the result of using the same design tools rather than any direct emulation or influence between the 2 sites. Once the 2-dimensional site design had been established, the designer had to work out how to make it 3-dimensional. When interrogating the design processes involved, we work from the basic principle that the 3-dimensional form of vaults at this period is dependent on 5 factors. This is a recap of what Nick just mentioned. There's the 2-dimensional pattern of the ribs, the height at which the ribs spring, known as the impost, the height of the apexes of the ribs, the radius of the ribs, and the position of the centre of the arc of the rib. Each of these factors could be used as a starting point, which then limits the options available for the others. Once 4 out of the 5 factors have been fixed, the 5th automatically follows. Some of these elements could be fixed by the pre-existing architecture. For example, you'll recall that the bay length and widths were based on the root 2 rectangle. Our data reveal that this was also true of the bay's height, meaning that this concept may have determined the height of the vault. Alternatively, the height could have been supplied by the apex of the east window, which might itself have been fixed by the √2 rectangle proportion. For the transverse ribs, therefore, the known elements are as follows: the length of the rib in 2 dimensions on the plan, the location on the plan of the springing and the apex, the height of the apex. And we've also identified from our research that medieval designers preferred, where possible, to locate the centre of the rib's curvature on the impost line, such that this often became a fixed point, and it is for the transverse arches at Nantwich. In this scenario, then, the unknown element is the radius of the rib. Now, this could be found working from the known elements, using what we've called the chord method. To do this, you can do it in 2 dimensions on the tracing floor. You first draw a line between the springing point and the apex. Then draw a line at right angles to the first line, halfway along its length. The point at which this line crosses the impost line is the position of the centre. Then the distance between this point and the springing and this point and the apex becomes the radius. So this is how the radius of the transverse ribs at Nantwich was probably worked out. By following similar processes for all the ribs at Nantwich, we can create a hypothetical model of the vault in 3 dimensions. We can then overlay our hypothetical model over our original traced model to check for conformity. And again, we're pretty happy with this result. We can also use the fixed elements model to create hypothetical designs for vaults which have been demolished or were never built. And to show you how, I'll pass back to Nick.
Thanks, Alex. So we'll finish by having a discussion of the partially constructed or perhaps partially destroyed 14th century vaults in the north transept. So what we can see here are springing stones. Hopefully you can see those highlights. So these are in situ and they're where the individual ribs spring from. We also see the bounding wall arches, so they're also in situ. So our question was, could we postulate simulations of the intended design using the existing architecture that's at Nantwich, as well as contemporary examples? So this type of research, you have to be particularly careful about being transparent to your audience because of the fact we're dealing with either destroyed or unbuilt architecture. So we've adopted a framework and colour coding system based on the work of Karen Kenzek and Mike Masouche. So hopefully this will become clear over the coming slides, but just to set the scene, if we draw a rib in green, that means we've deduced directly from the built architecture. If we use amber, it's an analogy derived from secondary sources, such as contemporary designs. And if we draw a rib in red, it means we've made an assumption that we know something had to be in place, but we can't substantiate it in a different way. So green, most confidence, red, least confidence. And adding to that, we have ribs in blue. That means that they're already there in the vault. And finally, we're using purple to show our original tracings in this instance. So here you can see these are the traced ribs of the north transept. So moving left to right, we have 2 sectional views. Third along, we have a plan of the bay. And then on the right-hand side, we have a 3-dimensional view. And then the image on the bottom right, you can just see highlighted where we've traced those stubs of the Springer stones. And what we've done here is we've taken the tracing and then we've extended the lines out of the missing ribs to see where they would end up. And it's really important to point out here that because we're only tracing a very small portion of some of these ribs, if we get that even a little bit out, it's going to be amplified further along the rib. So it means that the apex points that are missing, they're up for grabs really in terms of where they sit. So we'll go through the process Alex just described in the chancel, but we'll do this a little bit differently because it doesn't exist here. But looking first at the 2D process with extended lines in plan of the north chancel, we start with the bounding bay. So that's the bounding wall ribs that are already there. Next, we think the diagonals were added, and then the ridges, the ridges by joining opposite midpoints. And next, we think that they used a variation of the starcut where they add chevrons, so corner to opposite midpoint and back again in both directions. And we think this could be one of the ways in which the plan of the north transept was set out. And this is it overlaid with those extended traced lines. And if we look, we weren't that happy with the point in which the intermediate ribs, the tiercerons, how our hypothesis aligns with the trace lines themselves. So we wanted to come back to that. And here's our levels of confidence. So back to that chart a few slides back. So blue, they're the bounding ribs shown at the edges, and then we're very confident of the diagonals because they have to cross in the center. Likewise with the ridges, they also have to meet in the center, hence why these are all shown in green, but amber because we're less confident in these tierceron ribs. So as I said, we wanted to have another go to see if there was a better way of laying this out in plan. So starting again from the bounding bay, diagonals the same as last time, ridges same as last time, but instead we create a circle with its center point at the midpoint, and where that crosses with the ridge line, you can see here the red dots, we think that is the end point of the tiercerons in plan. And here you can see now the overlay, and we're much happier with that in terms of its alignment. And again, these are our levels of confidence. You'll notice that the tiercerons are still shown in orange. So although we are happier with this as a hypothesis, we're still not 100% sure. So we couldn't say to the public that we have a high level of confidence in that setup. And there you can see at the top, this is the first option, and to the bottom, the second option, which shows that better alignment. So we therefore used option 2 to carry on and to project this into 3 dimensions. So here's a recap. Here are the trace lines that have been extended. And here we go with the 3D hypothesis. So we know that the wall ribs are in place, they're in blue. And next we add the diagonal ribs, which we're very confident of their positions in plan and their central apex. Similarly, we're confident that the shorter transverse ridge rib is correct, given the existence of the start of these ribs in the vault and then need to meet the diagonals at the center of the bay. So for the first 3D option, we hypothesized that the longitudinal ridge rib was horizontal, given the similarity between the apex heights for the tiercerons, that's 3.56 meters, the diagonal ribs at 3.3 meters, and the transverse wall ribs at 3.53 meters. A horizontal longitudinal ridge rib is therefore used between the central apex of the bay and the tierceron apex. Consequently, the longitudinal ridge rib between the tierceron apex and the longitudinal wall arch apex has to curve down considerably, and you can see that shown here in red. Now, this contradicts the existing built fabric. Here we can see the start of the ridge ribs in the north transept. So hopefully you can see those circled and highlighted in red. Now, if we have a look at those, this is in the digital model. The evidence suggests that these are being projected out either horizontally or something that is very close to horizontally. So if we go back, this idea that they have quite a steep curvature to them, it just wouldn't work. So at this stage, we abandoned option 1. So moving on to option 2, we instead assumed a near horizontal longitudinal ridge rib with this shallow curvature to it. And we start to see support for this at other contemporary vaults in the country. Probably the most notable one for this is the chancel itself at Nantwich. So you can see this shallowly curved ridge line running across the bay. We find this as a design method at Ely in the Lady Chapel, also the Lady Chapel at Lichfield, as well as the nave at Worcester. But we wanted to investigate a third option, and this is where we have a horizontal ridgeline coming through. And this becomes curved as it reaches the geometry of the tiercerons. So the longitudinal ridge therefore needs to be designed to incorporate this new lower apex. Basically, what we've got here is something known as a tunnel vault. And we see lots of examples of this again. We see it in the choirs of Gloucester and Wells and the naves of Tewkesbury and Nantwich St Mary. So of the three options, we're most confident in option 3. And that's again because of the appearance of these short starting points for the ridge ribs, and they appear to be horizontal, if not near horizontal, as in option 2. But the evidence suggests that they were more than likely horizontal. And again, to reaffirm, because we can see this happening at other sites in England, it would be a logical way of designing the north transept vault. So this is just some dissemination work that we did following our research in the north transept. So we were able to 3D print a skeleton vault using the 3 different options. So if we weren't in the middle of a pandemic, we would have been delivering this talk to you in person, and we would have been able to give you this model, and you can kind of see for yourself what the 3 different options look like. And we also produce digital models as well, so that you can explore them online. And we'll give you some links to some more of our digital models at the end of the talk. So I'll now hand back to Alex for some concluding remarks.
Thanks very much, Nick. Well, we hope you've enjoyed our talk. We're very happy to take questions at the end. We also hope that you come back and join us in 3 weeks' time for the workshop. If you sign up for this before next week, you'll get a workshop pack with your compasses and your pencils and pieces of paper. But if you can't manage to, so you can sign up via Eventbrite to that. If you don't manage to, you can still sign up as long as there's space on the workshop. But please sign up within the next week, and then you can get the pack. We also have a book coming out later in the summer and an exhibition on our website. Again, we were hoping this would be in reality, but we're doing some really exciting things virtually because of the pandemic. So do look at our website, which is tracingthepast.org.uk. Do sign up for our newsletter to find out more about our project. That's either on the QR code on the screen, or you can do it via our website. And our website is soon due for a relaunch. So again, watch this space. Thank you very much.
The other element we'd like to just draw your attention to is we have a feedback form, and we'd very much appreciate your feedback on this talk. So if you have a spare 2 to 5 minutes afterwards, we'd really appreciate it if you could just fill out that information. Thank you very much. Do we have any questions?